Well, hello, greetings. Light. This is one of the most fundamental of the senses and one which we are involved with as visual artists. There are other people who um, do musical art. The chefs work with taste. The perfumers work with smell. But we are the guys who work with light and vision. If you think of waking up in a strange place, like in a dark, moonless night in the Karoo, you can be so lost you can get lost in the back passage of your own house. Ask me, I've done it. Light is very important. Now, the goal of this talk is to give us a high level overview of the science of light and a basic understanding of the human visual system, which is similar to the visual system of most animals. We'll be talking about physics, photons, and the history of the scientific endeavors of many very clever men who've worked over the centuries to figure out, and women, uh, how light works. What is light? Well, this is a pretty profound question and has been asked by people for thousands of years. Um, and I'm sure we have ourselves, if you look at the sun, the moon, the stars at night, a candle flame, a fire, what is this thing that we know we need it to see? We see light and darkness. You know, if we look back in old texts, if we look, for example, in the book of Genesis, we can see that the ancient Hebrews pretty much had an idea of how important light was and its very fundamental nature. We read there, light was the first of the created things. And God said, let there be light. And there was light. And I guess that would correspond today to the instance after the Big Bang when photons first appeared. And they were the first things created also after the photons matter kind of condensed out of the photon soup, I guess. If we look back at the ancient Greek philosophers, among the earliest recorded ones we have was a guy called Empedocles, about the 5th century BC. He thought that light was rays coming out of the eye. And this interacted with, they knew that you needed light like sunlight or a flame to see, but they thought there was some kind of fire in the eye that came out and interacted with the object that you were looking at and the light. Later on, we had the atomists, Democritus, who thought everything was made of atoms. He also thought light was made of atoms, tiny little things. And he envisaged this thing called an idola. My Greek pronunciation is not that hot, but it's something like this. And the idola was an extremely thin image that peeled off something you were looking at and flew through the air and came into your eyeball and rested on the back of your eye. So that was similar to, I guess, what we see today if we look at photons. But we'll come around a bit later to see that the idea of things coming out of your eye is not so preposterous if we run time backwards. Then, the photon coming into the eye as time goes forwards is the same as the photon coming out of your eye as time goes backwards and flying back up into space and onto a star. Anyway, and then Aristotle thought, the medium was very important that you were looking through, and it kind of enabled vision, and it changed nature somehow to enable you to see things when light was around. Euclid and Plato. Well, Euclid was a geometer, and he knew that lights traveled in straight lines. And in the 2nd century AD, old Ptolemy did experiments apparently with refraction. He I think the ancient Greeks had a thing called seeing stones, which were kind of either blobs of glass or like a primitive magnifying glass. Okay, so light helps us to see. We need it to see. It's composed of particles or waves of electromagnetic energy. And these light comes in single packets. And the name of a packet of light is a photon, which comes from the Greek word for light, photos. And your eye, if it's properly dark adapted, can detect a single photon. Now, on this slide, we have the sun coming in through a window here, and here's my hand holding a glass prism. The light comes in, is bent by the prism and separated into its rainbow of colors, which are showing up on the wall there. Here I've taken a photo of the rainbow and zoomed in on it. This picture doesn't do a real rainbow justice. Your eye gives a much more pleasing picture than this photograph. A rainbow is many prisms inside, many drops, and each drop acts like a single prism. The rainbow always occurs with the sun behind you. So you would be standing here, the sun comes along here, you're looking toward the rain. This is the outer rainbow with two bounces inside the raindrop. The colors are inverted. If there's just one bounce inside the raindrop, that's the primary main rainbow. Now we can take a prism, like we saw in the previous slide, and build it into a little apparatus, a little scientific instrument to help us measure things with light. Light is very sensitive and very useful. You can, for example, measure what gases are in a cloud of smoke coming out of a factory chimney by bouncing light off that cloud of smoke. You can measure what is in a sample of liquid or gas by using this device. So how it works is you've got a source of light, say the sun or some kind of lamp. You pass the source of light through a slit, a little entrance slit. Then you've got a little sliver of white light coming here. Then you have something called a dispersion device here. The original ones were all prisms, but you can also use a thing called a diffraction grating, which is many very fine lines ruled together, and they also have the effect of splitting up the light, similar to how you see on a CD. If you look at a CD surface in light, it's because there are many very fine lines there. It splits the light into different colors. So now the light, you've got the red and you've got the purple, and then you have another slit at the back side of this rainbow, and by moving the slit, you can choose which color you want. Do you want purple? Do you want yellow? Here we have selected a beam of green, and we pass it through our sample of liquid or gas, and then at the far end we have a detector. Then by moving the slit, we can measure how much power goes through in the purple, how much power goes through in the green, and so on. And we will get what's called a spectrum of the light coming out. And every element and every compound has a unique spectrum, like a fingerprint, that we can use to identify various different atoms and compounds. Now, if we take our little spectrometer that we built on the last slide and we scan across the wavelength of sunlight, we will see a spectrum that looks like this red band here. If we were on the space shuttle or somewhere far above the atmosphere, we would look at a spectrum that looked like this yellow band. The gray line that we see is the theoretical distribution of sunlight from the sun. The surface of the sun is about 5,000 degrees. It's called the black body spectrum. It's not really black. The black body is just the name of a scientific theory of a black box where all the electrons and photons and atoms inside the black box are all in equilibrium with each other. And it has a theoretical distribution which matches very well with what we see from the sunlight, and it enables us actually to tell the temperature of the heat of the surface of the sun from this peak. The peak is there for a 5,000 degree object. Now, as we spoke in the last slide, the absorption bands, the fingerprints of the sample that the sunlight has gone through, and these little lines here, there's the oxygen has absorbed there, water has absorbed there, and here, carbon dioxide has absorbed here, ozone, O3 has absorbed here in the ultraviolet. And the wavelengths here of light, the light that we can see, is here from about 400 to 700 nanometers. A nanometer is a billionth, 9 zeros of a meter. So that is 1,000 nanometers. And another way of saying that is it's 1 micron. A micron is a millionth of a meter, or 1,000th of a millimeter. So here your eyeball is most sensitive to this portion of the green here. Here's another little graph showing the spectrum. The green is what you can see best. Your eyeball is so well adapted to this sunlight, the peak of the sunlight coming through. Interestingly enough, the helium, the gas that we fill party balloons with, had little lines here, even if you measure at the top of the atmosphere, that were first observed in the solar spectrum. They were not observed of any gas or anything on Earth. And so the people postulated that it was something present in the sun that they had not yet seen on Earth. And that's why it's called helium. Okay, so about 40% of the light coming from the sun is here in the visible band. The rest is in the infrared. You can feel this when you walk outside. The power coming in from the sun is about 1.3 kilowatts per square meter. At the bottom of the atmosphere where we live, it's about 1 kilowatt per square meter. Now this graph just gives us an idea of how sunlight comes through the atmosphere. This here is a log scale. The wavelength gets a factor 10 more every time. You've got 1 nanometer, 10 nanometers, 100 nanometers. A normal scale of a graph goes like 1, 2, 3, 4, etc. But this enables us to span a very wide range of wavelengths. We can see here these very short wavelengths are the gamma rays and X-rays and extreme ultraviolet. Luckily for us, these very energetic rays are blocked by the atmosphere. Otherwise, it would cook us alive and be very bad for us. The most energetic rays that can get into the atmosphere are the visible. And there sits our eyeball right at the bottom of the atmosphere, just right, sort of Goldilocks-ish. And here we've got the infrared stuff, about 1 micron, 10 micron. And this is also blocked by the atmosphere. The only atmosphere that is not blocked is about 10 centimeters, 1 meter. You get up to the longer wavelengths, it's also blocked by the atmosphere. This is a little window that the radio astronomers can use to study the universe without having to put up satellites above the atmosphere. Okay. Now light shows quite a few different behaviors. Among them, reflection, refraction, diffusion, and scattering, which I will talk about in another slide. Reflection, we all know about reflection. For example, here's a lovely picture of a little river in the early morning that's very calm, and my dog. And you can see reflected in the surface of the water the clouds and the mountains, especially far away. You get different types of reflection. You get the very smooth specular reflection. That's from the Latin word speculum, which means a mirror, where you get an image. You get diffuse reflection, for example, of a snowbank or a cloud, where every particle bouncing off comes in a different direction. And you'll have no image there, you'll just have a brightness. We have refraction, where the light comes into something denser, like a glass prism. It gets bent and slows down slightly. The blue light slows down more than the red. And so it splits out and we have our little rainbow coming out the other side of the prism. If we look at a ray of light coming into a more dense medium here, it gets refracted, it gets bent at the surface. Some goes into the glass and some bounces off. Also, the water is the same. Some goes in and some bounces off. And it depends on your angle. We know this instinctively. If you're looking far away, like at the surface of water, most of the light will be bounced off. If you want to look into a pond or something, you must stand almost vertically and look downwards. When you look down, you'll see more clearly what's underneath the surface. But even if you look straight down, some still gets reflected. And we'll look at that in the next slide. Another thing we see is diffusion. Because light is a wave, this is an example shown with a water ripple tank. It's not light, but it illustrates the principle. If you have a whole lot of waves coming here and they come to an aperture, for example, a harbor wall, the wave comes into the harbor. If the aperture, if the size of this opening is large compared to the wavelength, that's the trough to trough distance of the waves, then the waves are mainly stay plane wave as they go forward. They bend a little bit at the edges, but they stay mainly plane. However, if the gap, if the hole is small compared to the wavelength, then you get almost like round wave fronts occurring here. And this is called diffusion. And ironically enough, if you've got a laser beam, even laser beams show this diffusion, the spreading out. And if you want to make a laser beam spread out less, for example, you want to shine a laser all the way to the moon, the trick is to make the aperture bigger. So you put the laser through a thing called a reverse telescope, which makes the laser beam bigger, and then it spreads out less. Now, even a perfectly clean pane of glass will reflect about 5% of light at the front surface and 5% at the back surface. So only about 90% of the light coming onto a sheet of glass like a window will go through the glass. And I've got a picture here of me inside my study at dusk. You can see this picture of me, and there's still a little bit of the scenery outside. And my chair's on my stoop and so on. So even in a bright daylight, when you look out your window, your 10% of the image of you will be on that glass, but you usually don't notice it because the light coming from outside is so bright. But on a dark evening, you see yourself reflected in that window. Now, this reflection is a problem if you've got many lenses. Imagine you've got a long telephoto lens with many surfaces. And on every surface, you lose 5%. And you've got all those reflections inside your lens or telescope mucking up the image. So you can fix this with anti-reflective coatings, which is another bit of optical wizardry. And these anti-reflective coatings are usually optimized for the green. So a little bit of red on the one end of the spectrum and a little bit of blue leaks through, and giving such lenses often a purple tint, or sometimes even dark glasses or glasses that have been optimized for anti-reflection have a bluish or a purple tint. Okay, now we're going to talk about total internal reflection, which is another little wrinkle on a reflection. If we have a source of light, say inside a glass block, and we shine it upwards, most of the light will just go straight out into the atmosphere. As we angle the light more and more, you see it gets bent, refracted. Here, more is reflected, and the refraction gets closer and closer to the glass surface. Later on, we get to an angle where this refraction can't be refracted anymore, and you get total internal reflection. Everything is reflected inside the glass or the water. Here's an example of a swimmer, and looking inside the pool, you can look up through that section and right here, but all these other places, we see a reflection on the surface of the pool of the swimmer. And a fish has this problem. It can only look up through a certain, like us trying to look into a pond, the fish can only look up through a certain little hole, but it is restricted more than we are looking down into the pond because of total internal reflection. Here's another example of a little laser beam bouncing inside a slab of glass, which is used sometimes for signage or for fiber optics, where we have fiber optics are a little glass fiber about thinner than a human hair, and laser beams are shone into this thing and switched on and off very fast, and this can transmit information over continents and into your home. You can watch a cat or someone singing some video in Korean or something, all due to fiber optics, lasers, and little light bouncing inside little. And here is a prism using total internal reflection, which is often used in binoculars rather than a silvered mirror. This prism will never decay, the silver won't fade. It will always, provided the surface is kept clean, will always reflect like it did on the day it was new. Now, here's a diffusion versus distance demo. What we have here, I've cut a little triangular hole in a piece of paper. And when the piece of paper is near the surface where it's casting a shadow, you can see quite a sharp triangle there. And as we move the paper further away from the surface where the shadow is cast, we can see that the hole gets more and more blurry. And as we get further up, the hole almost looks like a little round circle. And it is a round circle because it's an image of the sun. So this isn't really diffusion, it's more a pinhole camera effect of the sun. It's because the sun is round that it turns round. But you can see all these images have got more blurry the further away you are. And this is something you must observe when you're painting something. Shadows aren't sharp as they are when the object casting the shadow is close to the surface on which the shadow is cast. And here's another little demo. This is taken during a solar eclipse of the shadows under a tree. And I don't know if you've noticed, but next time you're under a tree and the sun is shining, look down at all the little images and you will see that they are all little round spheres, circles. They are all images of the sun. So next time there's a partial solar eclipse, rather than trying to look up at the sun, rather cut a little hole in a piece of cardboard and look at the shadow, and you can see clearly the moon coming across the surface of the sun. You will see the half moon appearing there like this. By just looking at the shadow, you don't have to try and damage your eyes looking straight up into the sun. Now, another fundamental thing that light does, and that we really notice especially over longer distances, is scattering. And this is very important for the landscape painter. I remember when I was younger reading an art book that my parents gave me, and it described, if you're looking at a landscape over several miles, that the atmosphere was like a series of veils drawn in the sky, and things further away got fainter and fainter and less saturated. And this is one way of looking at it. But what's really happening is that sunlight, is being scattered off the atmosphere. If we look, say, at this bit here, we can see this is a photo of the Cederberg, this one. And you can see as we go further away, it gets bluer and bluer until the colors kind of fade almost into the distance. This is an older camera. I think this photo was taken about 15 years ago. And the more modern camera might show you more detail in that far distance. But anyway, here we see a picture in the Greyton area. It's not as much blueness, but you can see the same effects here as you get further away. Now what's happening here, the sunlight is coming down. So it's coming down from here. Is it from here, from this side? Yep. And bouncing off the molecules in the atmosphere. If we look here on the moon, the sky is completely black. Why is the sky blue? Sunlight bounces off the atoms in the atmosphere and then comes into your eyeball. And because the atoms in the atmosphere scatter more blue light than red, you see the sky is blue. And you know, the sunlight is coming down here between these mountains, and it bounces off the atmosphere, comes into your eye, and adds a blue component to the light bouncing off that far mountain. Another thing that I've really noticed in the Cape Mountains, and I think, you know, South Africa has a beautiful quality of light that you don't see, for example, in Europe. You don't have mountains and you don't have the long view often, you know, it's just grey and foggy and so on. But here, you know, you can see, I know in the Kamdeboer you can see about 80 kilometers, you know, to certain mountains. And another thing you can see here, look there, you see that slight lightness above the ridge. You see the ridge is slightly darker than the air behind it. And here as well, you can see a dark ridge, and then behind it you see that lightness there. And the lightness is lighter than the tip of the ridge. And I think this is mainly due to water vapor in that dell or valley, either water vapor or dust. But it's also a scattering component that affects what you see. And I just love it. I just love it. I've been looking at it for the last 40 or 50 years and enjoying it and trying to capture spots of it in paintings. Now, the main type of scattering that gives us the blue sky is Rayleigh scattering, named after this dude who was Lord Rayleigh, who won the Nobel Prize in 1904, partially for his explanation of why the sky is blue. And it occurs when the scattering particle is much smaller than the wavelength of light. And it's mainly the atoms of the sky, the oxygen and the nitrogen in the atmosphere, that scatter the sky. And what happens with Rayleigh scattering, the scattering is inversely proportional to the fourth power of the wavelength. So between the red that we can see and the blue that we can see, there's 10 times more blue scattered than red. And this is why the sky is blue. So next time your child or grandchild asks you, why is the sky blue? You can say, my dear child, it's because of Rayleigh scattering goes inversely with the fourth power of the wavelength, of course. Anyway, you also get Mie scattering, named after Gustav Mie, a German physicist, when you've got much larger particles like raindrops or dust. And this isn't so dependent on wavelength. So because, the Rayleigh scattering gives us blue sky and red sunsets. And here's a little thing, you know, there's the observer, that's you standing there. The sunlight comes along, it bounces everywhere, but it really goes, the blue comes much more into your eyeball than the red. Now, scattered light is also polarized. I don't think you can really use this in a painting, but it's just an interesting fact. If you take a picture of the sky with a polarizing filter, you can see a difference as you rotate the polarizing filter. And I think some birds and bees and homing pigeons and stuff use this polarization to orientate themselves. Another little interesting fact is that reflected light is also polarized. Light reflected off a road surface or off water is polarized, and that's why polarized sunglasses are so effective. If you tilt your head 90 degrees, you'll see your polarized sunglasses are not really so good. But if you've got them horizontal, like the level of the water, then that's pretty good. Okay, here are some more fun photon facts. Um, yep, photon is a truly fundamental particle. It's not like an atom that's got protons and neutrons and electrons. It is just it. There's nothing underneath the photon. It is just a final little blip. It's responsible for electromagnetism, electricity, magnetism, radio, light, electricity, and it's what holds our bodies together. There's electrical charges holding the positives and negatives together. And it's one of the few fundamental particles of the Standard Model. There are about 6 baryons and a couple of bosons, not to mention the bosons. But anyway, so you get quarks and you get the electron and you get the photon and then you get the neutrinos and things like that. Anyway, there are not that many fundamental particles in the Standard Model, but the photon is one of them. Photon has momentum and mass while it's moving. When it stops moving, it ceases to exist. So because a photon's got momentum, it's affected by gravity, but only very slightly because it doesn't have much momentum. But as it's traveling past a heavy object like a star or a galaxy, its path will be slightly bent. As an example of light being bent by gravity, here we've got a little picture of what's called an Einstein ring, which is a whole galaxy. The blue galaxy is a ring, which is actually one blob behind this bright blob in the middle of the picture. And the fact that, see if I can get this, yeah, there's the middle blob, and this is the Einstein ring. So that picture of the galaxy has been turned, has come toward the star and been bent around the star into this ring. The first observation of this kind of gravitational bending was made by British astronomer Arthur Eddington in about just around the time of the First World War. There was an expedition to some island where they watched an eclipse, and they detected the slight bending of the light from some stars that passed near the edge of the sun during the eclipse. And this was one of the first experimental confirmations of Einstein's theory of relativity, which predicted this bending of light by gravity. Okay, so there you can see it physically. We've got very, very fine telescopes that can see things like this. Yep, now I thought I'd just talk a little bit about lasers because I spent 5 years of my young life diddling around with lasers, which I quite enjoyed. And yeah, because some people find them interesting. So I'll just give you a little diversion onto lasers, which doesn't have much to do with painting, but just general interest. A laser, the word laser stands for light amplification by stimulated emission of radiation. Before the maser, there was the laser, there was the maser, which stood for microwave amplification by stimulated emission of radiation. And mazes were built before lasers. They were slightly easier to build. But lasers really captured the public imagination because you can see this beam of light shining down the corridor or way out into the space. And it just captures the imagination because it's a Star Wars-ish type of thing. Lasers come about because to do it, you need a light amplification. That's part of it. And it's very difficult to amplify light. You can make light, with an incandescent bulb or an LED or a fire or a candle. But to amplify light is quite a trick. And it only became possible in the last, I would say, 50 to 70 years. Before that, it was impossible. Although it was predicted by Einstein in about 1919, it didn't become physically practical until the 1960s. So what a laser does, you've got to get light to amplify. You need an amplifying medium, something that when you put some light in, you're going to get more light out. And this is difficult to achieve because, as we know, most things absorb light. The atmosphere absorbs light, water. You shine a light on a carpet, you shine a light on your dog, you shine a light on anything, it gets absorbed, it doesn't get more. But there's special physical tricks you can do to make certain things amplify light. I can maybe go into that a little bit more later. But usually the thing that will amplify light only is an amplifier for a very short time. You've got to pump it and excite it so it's got some energy sitting there waiting to give to the light. And it sits there and the energy is usually wants to go somewhere else. And it's waiting for a hot date. And if the hot date doesn't arrive, it goes somewhere else. And so it sits there, and it usually only sits for like a billionth of a second or a few hundred microseconds. And if you don't stimulate it, the energy decays into heat or something. So the first lasers were pulsed lasers, and after that, they learned how to make them continuous. So every photon coming out is an exact copy of a photon going in. So you have photons coming in on the left. They sort of tickle this excited thing, and the excited thing gives them another copy of themselves. And they come out, they've got the same phase, wavelength, direction, everything. And they come out as an amplified copy of what comes in. So as I said, it's difficult to produce an amplifying medium, and that's only been possible in the last like 80 years. Sounds quite a long time now, 80 years, but to me it's just the other day. Okay. And as I said, the first lasers were pulsed, but now you get continuous wave lasers as well. If you're doing a pulsed laser, you can get very, very short pulses, down to the nanoseconds, which is a second with, a billionth of a second. And it's quite easy to get a peak power equivalent to like the Coburg power station, a gigawatt pulsed power, but it's only for a nanosecond. So you can't really power your home with it or anything, but you can have very high power for a very short time. And with high peak power, you don't need gigawatts, just some megawatts or even kind of kilowatts. You can cause air breakdown. If you focus the laser down, you get like a big spark occurring in the middle of the air, like lightning, but it's just, especially if you've got an infrared laser, which you can't see, you can focus this down and you get like a big spark in the air there and a big crackle, and it's quite spectacular. I remember once when I was a young scientist, there was a kind of the head of the institute where we were walking around, and as a kind of demo, I fired this laser and I had a little reflective mirror, like this, and I held it in front of the laser beam, and it focused the laser beam just in front of him, and it made a big snap crackle in front of him, and he jumped back and said "Bliksem" or something like that. Anyway, lasers are very useful, cutting, medical. You can do surgery with them, diagnostics. You can and fiber optic communication. Many uses of lasers. Okay. Now a laser is only visible if it's bouncing off something. We can see here I'm shining one of these little green laser pointers one night through my yard and then onto a tree. Here I'm shining it a bit further onto a house, onto something on the mountain about 1 kilometer away. And you can see the laser beam here. You see these little speckles like here and there. That is the laser beam bouncing off dust in the air. You can see the path of the beam. If we were shining this beam like on the moon, you would see nothing until it hit something in the distance. And so again, this is the effect of dust and stuff in the atmosphere. And this is a problem if you've got a very high power laser. A very high power laser will scatter and bounce off stuff in the atmosphere which is not perfectly clear and degrade and not reach the target as you want. I remember once when they were doing a TV program about lasers at CSR when I was young, and the TV crew came in there and they had all these nice mirrors and lasers and stuff in this lab. The TV crew wanted to see the laser shining through the air like this. So they filled up the whole lab. They brought a bee smoker along with them that, is full of burning sacking inside. And they puffed this bee smoker smoke all through the lab and probably damaged a whole lot of these fancy mirrors that the laser scientists had. But they could see the laser beam then on their TV program, which was all that they were worried about. Anyway, that's that. Now, light is extremely fast. I'm sure you all know this. You've seen like at an athletics meeting or something, the guy fires a starting gun across the field. You see the puff of smoke before you hear the shot. The light signal gets to you before the sound. I remember learning about this in primary school. The light goes around the world 7.5 times in 1 second. That's pretty fast. And the speed is, 1 nanosecond per foot or 3 nanoseconds per meter. You can use this to measure the distance to things. If you've got a laser rangefinder, bounces a laser off the target and counts how many nanoseconds there and back. And the speed of light is the ultimate speed limit of the universe. As we know from the theory of relativity, nothing can go faster than light. You can put more energy into a particle, but as you do, the photon can go at the speed of light, but anything with rest mass cannot get to the speed of light. If you put more energy into it, it just gets heavier and heavier at E equals mc squared. So you get it up to 99% of the speed of light, then you can put another double its energy, it'll go up to 99.5% of the speed of light. Double energy again, 99.7%. It just never gets to 100% of the speed of light. You can make the particles a lot heavier, and you can see that happening like at CERN with these big atom smashers. They've got to ramp up the magnets on that ring as they accelerate the particles. The particles aren't getting much faster, but they're getting heavier and heavier. And so to keep them in their orbit, they've got to ramp up the magnets. The speed of light is also the ultimate kind of conversion factor between space and time, which is quite profound. If you think about it, you're in the middle of space and someone sends you a signal, do you know if it's far? Signal takes a long time to get to you. Do you know if it's far or the light is going slowly, or the time being messed with? So the speed of light is somehow this yardstick that you use to measure space and time. It's quite a thing. Okay. Next slide. Shoot, how do I do that? Now, measuring the speed of light is actually pretty difficult. And the first recorded attempt, I think, to measure the speed of light was Galileo Galilei, who had an assistant on a faraway hill with a lantern covered with a black cloth. And he had a lantern covered with a black cloth. And he whipped the cloth off his lantern and waited for his assistant to see the light and whipped the cloth of his lantern. And then he tried to record the time different distance for the light to go to the hill and back, which, as we've seen, would be milliseconds or microseconds. And Galileo concluded that it was within the shortest time that he could measure, which was human reaction time, about a 0.2 of a second or something. So he kind of realized the speed is either infinite or faster than he could measure. The first time the speed of light was actually measured came about by accident by this guy, Ole Romer, who was the Astronomer Royal of Norway. And he was trying to use the eclipses of one of Jupiter's moons as a kind of clock in the sky for navigation purposes, before they had reliable seagoing chronometers. You know, a chronometer is a very accurate clock. Sorry, I'll try and talk more slowly. So Jupiter's moon Io has an eclipse, goes around Jupiter once every 1.8 days. So they timed these eclipses and they thought they could use the timing of these as a very accurate clock. But he noticed if he did this over a period of a year, when the Earth was here, and especially when the Earth was going this way, the time between the eclipses got longer and longer. And as the Earth went from here to here, the time between the eclipses got shorter and shorter by about 20 minutes. That's the time difference he measured. And he reckoned this is the time that light takes to get from, when the Earth is in this position of its orbit to that position of its orbit. So he reckoned that is the light speed across there is the accounts for the difference in the time of these things. Pretty darn clever to work that out. And he got an answer that was in the kind of right ballpark. They didn't know the exact